We're doing rotational equilibrium problems, statics. It's called statics from OpenStax physics. And I'm not sure why it's called statics, except that things are static, but I don't really like that. Rotational equilibrium, rigid body equilibrium is an even better one. Okay, so here's a problem I made up. The problems in the OpenStax physics textbook, I think, were a little lacking. No offense. So I'm just going to do my own problems here. This problem has, it's just a completely made up situation. There's a penguin, see, on a plank, see, and the penguin can walk out on this plank that's supported by this string and then a pin right here. Okay, now a pin, when we say a pin, that just means that, well, it doesn't really matter. It's a pin. It could move, but it does move. So the maximum tension in this string is 88 newtons. So the question is, how far can the penguin move out on the plank until the string breaks? So what's that distance x? This is a pretty difficult problem, and I think that it might even be impossible. I can't remember. I haven't solved it in a while. But let's just get to it. So we want to assume that the plank stays stationary. Now, if the plank stays stationary, then two things are true, which I'll write as three things. The three things that are true are F net in the x direction is 0. That's because the acceleration in the x direction is 0, so the net force in the x direction is 0. F net in the y direction is 0. Again, if it's not accelerating up or down, the acceleration has to be 0, so the net force has to be 0. And finally, the rotational equilibrium part, torque net O equals 0. So this is a thing that the book doesn't mention, but it's important. O is, you have to pick a point about which to calculate the torque. But it doesn't really matter where you pick it, right? Because if it's not rotating about that point, it's not rotating about that point, it's not rotating about that point. So it doesn't really matter. And the same is true for the net force in the x and y direction. You have to pick an x and a y direction, right? Okay. So I have those three equations, and of those three equations, what am I trying to find here, right? I know I have all these situations, but at the end, we've got to think. I'm trying to find that distance x. I'm trying to find that distance x because as that penguin moves further and further out, the tension in this is going to increase, and at some point it's going to get to 88 newtons, and that's the breaking point. So we want to use that to solve for x. Let's start off with a free body diagram, or we should say a rigid body diagram for the plank. So I want to draw all the forces acting on the plank, and I want to place them where those forces are applied. So the first thing, I'm going to draw this, I'm going to just put it like this, F wall. All right, the pin right here pushes on the plank, it has to. I don't really know exactly what that force is, and that's fine. Maybe we can find it. We could break that into a vertical and a horizontal component, but right now I'm just going to put it like that. No, I guess I should break it into a horizontal and vertical component, just because it'll be easier to set up these equations. So let's call this Fy and Fx. Next, I have the weight of the plank. So gravity pulls on the plank in all parts, but we can calculate it as though we're pulling at just one point, and that point is the center of mass. So since it's a uniform density rod, the center of mass is the center. So that's going to be right here, mass of the board, I called it, times g. And so if that's 2.5 meters, then that's 1.25 meters from the edge. Next, this one I'm going to treat. I actually have the normal force of the penguin pushing down on the plank. Okay, the gravitational force does not push down the plank. However, if I drew a force diagram for the penguin, I have the mass of the penguin times g, and then the normal force of the plank pushing on the board, pushing on the plank, the penguin. Okay, since the penguin's in equilibrium, those two have to be equal, and since the board pushes up with the force equal to mg, then the penguin pushes down with the force mass of the penguin g. So I'm going to put that on here, but I just want you to realize it's not actually the weight of the penguin. And we don't know where this is, so I'll just put it right here. Mass of the penguin g, and I don't know where that value is, x, I'll just put it right there. And then finally I have the tension, T, right there, and this angle is 50 degrees. Now, I already know how to solve the problem, okay? Hopefully that's not a surprise. But I'm going to set it up in a logical way. I'm going to write down these three equations first, because it's actually not, if I recall, not a terribly difficult problem. So let's write down this first one, F net in the x direction. Let's just write it as an equation. So what forces do I have acting in the x direction? Well, I don't know because I haven't picked an x direction. Let's pick this as the x direction and that as the y direction. That seems to make most sense. So what forces are there? There's only two forces in the x direction. I have the force from the wall, equals Fx, and then I have the horizontal component of the tension. So that's going to be this component right here. So that's a right triangle. The magnitude, the hypotenuse is the magnitude t. So this would be the adjacent side. So it's going to be, that's x, minus t cosine theta, and that's 0. I don't know fx. I don't know t. So, I mean, I know theta. That's the only thing I know in that equation. But that's what we're done anyway. It's good practice. Next, I'm going to write down the y equation, F net y. What forces are in the y equation, y direction? We'll have this force, Fy. And then I have these two forces pushing down. So minus mass of the board times g, minus mass of the penguin times g, because they're in the negative y direction. And then finally, I have a component of the tension. So that's going to be equal to the opposite side of this right triangle. So we're going to use the sine. Plus t sine theta equals 0. Notice in both of these cases, it doesn't matter where those forces are. It only matters which direction they are. We could draw this free body diagram as just a point in that case. The only one where it matters where they are is the torque. Torque net O. So we need to pick a point about which to calculate torque, and there's no wrong answer. Okay. But what you want to do is to pick a location that eliminates torque due to some forces. So if I pick, for instance, if I pick my center of the plank as my point O, then the gravitational force due to the mass of the board would have 0 torque because the R value is 0, the torque arm is 0. And so that wouldn't be in the equation. I wouldn't need to know it. Well, I know the mass, I know G, so I don't really care about getting rid of that. I want to get rid of the ones I don't care about and I don't know. And so that says, hey, if I pick that as my point O, then Fy and Fx both have a torque arm of 0, so the torque due to those two is 0, and they won't appear in the equation. I don't know what they are, and I don't care. Okay. So let's pick that. So that torque is 0, and that torque is 0. I'll just put them both as 0 right there. Now I can go through these other three forces and find their torques. So here I have this torque arm is 1.25 meters. It's half of the length. Let's just call that L for right now. So that's going to be L over 2. And then the force is mg. And remember, I guess I should say torque is R, F, R, what's the sign? Sine theta. So it's the force times the torque arm times the angle between the force and the torque arm. Here, theta is 90 degrees. Sine of 90 is 1. The torque arm's L over 2, and the force is mg. Now, I do need to say, is that a positive or negative torque? In general, if it's a clockwise torque would want to, by itself, would want to make this thing rotate clockwise. We can call that negative. If you want to call it clockwise positive, because clocks, that's fine. As long as you're consistent, you'll be fine. It's not technically correct because of something that we call the right-hand rule, but don't worry about that. So this will be a negative torque. It's going to be negative the force, mass of the board times G times L over 2 times sine of 90, which is 1. What about this torque? Well, it's also going to be negative. It would make the mass of the penguin, the weight of the penguin, would also make the board rotate in the clockwise direction, so it's going to be negative. Now, its torque arm is x. I don't know what that is, but I can write minus mass of the penguin times G times x, but I don't know what x is. And finally, I have the torque due to this tension right here. So I know the angle between R and F is theta, right? So I can use that. So let's just write that out, and it's going to have a torque arm of L. It would be a positive torque because it wants to make it rotate counterclockwise. Okay. So it's going to be plus T L sine theta. And all that has to equal 0. Which you can't see. Okay. So in this torque equation alone, I don't even actually need these two equations because I know that. Remember, if I have one equation and one unknown, I can solve that. So let's go through what I know. I know what 0 is. I know the mass of the board. I know G. I know L. I know 2. I know mass of penguin, G. I don't know X. I know the maximum tension. I know the length. And I know sine theta. So I can solve this equation for X. So let's just move this term to the other side. I get MPGX equals, and then what I have left is TL sine theta minus MBG L over 2. I'm going to divide both sides by mass of the penguin and G, and I get X. X is going to be TL sine theta over MP. I guess I should just, I'm trying to decide if I should factor out the G. No, that's fine. MPG, that's MPG minus MBG L over 2. Let's put in our values. So I know T, 88, 2.5, sine of 50, minus the mass of the board, which was 5 kilograms, times 9.8, times length over 2, so it's 1.25. Did I run out of room? I made it. Whew, okay. Divide all of that divided by the mass of the penguin, which is 11, times 9.8. Let's put it in the calculator. $88, 2.5 times 50 sine times 5 enter 9.8 times 1.25 times minus, and then divide by 11 and divide by 9.8. And I get 0.9, okay, it did work. I get X is 0.995. meters. So if the penguin's at that position, then the torque, the tension in the string is, the cable is 88 newtons exactly. If the penguin moves too far this way, that tension would have to increase to be greater than 88 newtons, and so according to what I said, it would break. And so the penguin couldn't go any further. Okay. Now, just as a bonus, I'm not going to do it, but as a bonus, once I know X, could I go back up here and solve for Fx and Fy? I could, right? Because up here, actually, I know Fx. I know T. I don't know Fx. I know T and cosine theta. I could get Fx. Right here, I know MB, G, MB. I know all these values. I could solve for Fy too. So you could do those if you wanted to. But the way we did this, we didn't need to know those. If I picked this as my location about which to calculate the torque, then I would actually have to first find those things. I'd have to find Fx, well, not Fx, because Fx would have a 0 torque, right? Because the torque arm is L over 2, but the angle is 180 degrees, which is 0. Sine is 180 is 0. So, okay. I like that problem. It was fun. Let's do another one.